Okay, again, can you guys hear me?
Yes, sir.
Yes, sir.
Okay, very good.
Sir, let me join with my laptop.
Yes. Can you guys see the screen? Hello.
Yes, sir.
Okay,
Yes, sir.
very good. Very good. Okay, so the objective of this lab will be is to simulate and analyze the behavior of plasmonic ring resonators. Okay, so what is the plasmonic ring resonator? We'll come to it shortly using the COMSOL multiphysics software. So COMSOL is a very new software for you. I think that almost none of you have used this one, right? The COMSOL software. Are you guys familiar with this software or not? I
No,
don't
sir.
I don't
No,
think
sir.
so. Yeah, okay. So some of you, when you are will do thesis in plasmonics or photonic, what is that called? PCF, photonic crystal fiber. If you take your thesis in this line, you will be using this COMSOL software frequently. Okay. So, and in this time, we'll be covering a little bit the theoretical aspects of the simulations and what the microring modulators are. Uh, and we'll simulate that microring resonator, and we'll understand the key theoretical aspects and interpret the simulation results. Okay. So these are the objectives of today's lab. But before going to the directly to the simulation, first, let me give you a little bit idea on COMSOL. Okay. So COMSOL is a very heavy software. All types of real world modeling and simulations can be done in COMSOL. Okay. As it is written here that COMSOL multiphysics is a versatile finite element software. What is finite element? We'll come back to it shortly. So it is used for modeling, simulating, and visualizing physics-based problem across science and engineering. So the application area involves like electromagnetism, then structural mechanics, heat transfer, fluid dynamics, and so on. Okay. So it also provides a user-friendly graphical interface, and what it basically does, that COMSOL in the background, you in COMSOL you draw structures, you do different types of simulations and all these things. But in the hindsight, in the background, what it does is that it solves various powerful numerical problems. Okay, so there are various types of numerical equations, differential equations, wave equations, particle equations, okay, pressure equations, all these things. So at the hindsight, what COMSOL does is that it solves those equation and gives you a result. Okay. So for example, here I've seen that said that the application area involves electromagnetism, structural mechanism. So for example, this is a heat temperature profile, okay, of a heat sink. Okay. These types of simulations, okay, this radiative heat transfer, these types of simulations are usually can be done in uh, COMSOL, okay. So as you can see, there is also another one. Let me see this one. You see these types of uh, real world objects can be simulated, and the results can be analyzed here, okay, using COMSOL. So this is actually a simulation of this bracket here. Uh, they're optimizing the shape here. Then there is structural mechanism. For example, this structure. This is a what is this called? A simple providing pressure here, and they are observing the deformation of this beam. Okay, so these are uh, civil engineering students usually do these types of, also the mechanical engineering students do these types of simulations in uh, COMSOL. Then, for example, if I look at, so we usually do these types of simulations. For example, mm, so these are nanostructures. Okay, we simulate this. We send lights through this. Okay, we'll be studying this shortly. So, but what I'm trying to say is that using COMSOL, you can do any types of real world. You can replicate any types of real world problems and simulate those things in COMSOL. Okay. So in today's lab, we'll be focusing on microring modulator. So what is a microring modulator? So let me show you a simple diagram of this microring modulator. So this is a very simple microring modulator. Okay. So this is the whole rectangle. It is the substrate. So in this lab, we'll be considering it as silver Ag, and this ring, this resonator ring. This is called a resonator ring. Uh, it will be air. Also, this waveguide. What is waveguide? We'll come back shortly. So this is also filled with air. So this is a simple microring modulator. So in real life, let me show you. So these are all microring modulators. Is there a 3D picture? So for example, this is, you see, this is a photonic integrated circuit. So there in that whole circuit, there is this portion. This portion is the what? Is our microring modulator. So the applications of microring modulators are vast. Okay, in various types of integrated circuits, these modulators are used. We pass light through the waveguides and observe the transmission spectrum through this for this microring modulator. So first thing is that what is a waveguide? Uh, you see, I've told you that this is a waveguide. Okay, so a waveguide is nothing but a pathway, okay, a medium for the light to pass. Okay, so if I give light in this port, the light will travel through this path. Okay, it provides a guiding medium, the waveguide. It guides your waves. It guides your optic light through it. That's why it is called waveguide. It's nothing but a simple structure through which light can pass. That is actually your waveguide. It lets you, it guides the light through it. So this is nothing but a waveguide. So waveguide does nothing but gives light a medium to cross. Okay, as you know, light can pass through air. Then you have this ring modulator. So this ring modulator actually plays a crucial role. It affects how light passes through this waveguide. Okay, so before that, let me tell you one more thing. Uh, So your ring modulator, what is the, so ultimately your what is your plasmonic ring modulator? It is a nanoscale structure in which light propagates along the metal. Okay, so this one is a metal, right? The silver is a metal, and this is air. This waveguide is filled with air. Air is what? A dielectric material. Also, this ring, it is also a dielectric material. So here the light is propagating along a metal dielectric interface. This is metal, this is uh, dielectric. There is an interface between this metal dielectric. Okay, this is dielectric and this is metal. So there is a metal dielectric interface. And when in nanoscale level, when light falls in this surface, it creates a evanescent wave, a standing evanescent wave, which actually with time it actually diminishes. Okay, so these are actually used. This is basically called a SPP. So when light falls in a metal dielectric medium, at the surface of this metal dielectric interface, this SPP is formed, and SPP usually passes through this waveguide. Okay, this SPP passes through this waveguide. So basically, when we are talking about light, we are actually meaning that SPP is traveling through this waveguide. So for now, you can consider SPP is nothing but it's a light. Okay, it's an electromagnetic wave that is passing through this waveguide. Now, an interesting thing happens to this waveguide when we place a micro ring here. That is, when we place a uh, ring modulator in this place. So, are you guys listening to me? Am I audible?
Yes, sir.
Okay, very good. So, are you guys understanding what I'm saying? If you have any questions, these things are a little bit advanced for you guys. You haven't studied yet electromagnetism and numeric methods, so it can be a little bit intimidating for you. So if you don't understand anything, just ask me. I'm trying to give you the simple idea. Okay, I'm not going too deep, just giving you a simple idea. All right. So if you are if you are not understanding anything, just ask me. Okay, I'll just try to give you a simple idea on this plasmonic structures. Okay. All right. Now see what happens actually. So this is a nanostructure, right? Nanoscale structure. So if I give light through this port, this is one port and this is another port. Okay. So my goal will be is to give light through this port and observe the output port. For example, if this the intensity, this is the power of the light is Pi here, and at the output of the waveguide, this is the waveguide, light will propagate through this waveguide. So at the output of the waveguide, the power will be having the light will be having a power of intensity that is P naught. Okay. So as you know, what is transmittance? When light falls, for example, this is a medium, this is a dielectric medium. Okay. This is an interface. So I'm giving light from from this point. So light falls on this surface. Some of the lights will get reflected, some will be refracted or transmitted, right? So the amount of light that is getting transmitted, that is called actually your transmittance. You know this, right? So transmittance is basically T is equals to P naught by Pi. Okay. So our goal is to observe this transmittance, that we are sending some light through the input port and the output port. We are observing some power. So from these two information, we'll get the transmittance, and then we'll observe the transmission spectra. Is this clear? So now what happens is that when we place a micro ring modulator, something interesting happens in the transmittance curve. So let me show you. See, when we are passing light through this waveguide, lights will get light will travel through this. Okay, light will travel through this waveguide. Okay, with the same intensity, with some intensity, it will travel through this waveguide, and at the output, we'll receive this uh, power, some intensity light. Okay, but what happens is that there is something called resonant condition. Okay, so what is resonant condition? So when we are saying that we are passing light, we are actually passing what? Some frequency light, right? For example, if I say I am sending microwave light, so it has some particular frequency, right? You guys know this, that light has some frequency, some wavelength associated with it. Do you guys know this? For example, see, this one is red. This color is red. What does this thing mean? The wavelength that corresponds to the red color is actually absorbed in this part, and all the lights are reflected. So that's why we see it as red, right? For example, this is blue. The blue, the blue spectrum of the light, that is the wavelength that corresponds to the color blue, is getting absorbed here, right? The point is, light is associated with some wavelength, that is lambda. Okay. When we are saying that we are actually giving light as an input, we are actually giving light a wavelength, and wave with certain wavelength. Is this clear? That means here We are providing light with certain wavelength. Is this clear? Okay. So when we are transmitting light through this wavelength, now if this wavelength is equals to twice pi r, r is the radius of this ring. Okay. If this wavelength of the light, if the wavelength of the light matches the circumference of the ring into eta. Eta means what? The refractive index of this ring. The refractive index of this ring is what? Eta. Okay. So if this value twice pi r eta is equal to this lambda, that is the length of this length of one cycle. Okay. If these two matches, what will happen is that the light will get coupled in this ring resonator. Okay. Now the light will not directly pass through this waveguide. Instead, some portion of the light will get the photons. Okay. Through basically it is done through quantum tunneling. Okay. Some photons, instead of going this way, they will jump to the ring resonator. Okay. They will jump to the ring resonator and starts to circulate the resonator. Okay. So please repeat the coupling part. Okay, see again. Uh, this is called the resonant condition. Okay, so when your uh, light has some particular wavelength. Okay, that is lambda. If the lambda is equals to this twice pi means what? The twice pi is what? The circumference. That is the length that light will travel. Okay, the length that light will travel. This is the whole length that the light will travel. If light enters this resonator, it will travel this whole path, right? So then what happens is that this is your twice pi r. Okay, that is the total circumference. So if light travels to this whole circumference into eta, eta is what? Your refractive index. So if the wavelength of the light is equal to this part, this value, that is the length into the refractive index, then resonant that then a particular phenomena happens that is called the light will be resonating in this uh, microring resonator. Okay, the resonance conditions occur for this condition. That is, for example, let's say the L and this value is, let's say, 200 nanometer. Let's say this value is 200 nanometer, and the wavelength of light that you are sending, okay, let's say it is 300 nanometer. Okay, so these two values doesn't match. These are not equal. So what will happen is that wavelength light, that is the 300 nanometer wavelength light, this 300 nanometer wavelength light will pass through this waveguide. Okay, and at the output you'll receive a high intensity light. But if this lambda is equals to 200 nanometer, this is a constant. This 200 nanometer is a constant, twice pi r into eta. Your radius of the ring resonator is constant. Your refractive index of this here is what? 1. Okay. So this is a constant value. So if your wavelength of the light 200 nanometer is equals to this value 200 nanometer. So what will happen now is that light instead of passing completely to this through this waveguide, some of the light will happen what? It will flow along the resonator. It's actually what happens is that some photons they jump to the from the waveguide, they jump to the uh, ring resonator. Okay, so this is actually done by means of quantum tunneling. I will not go into details on those things, but the for you, what is necessary is that when resonant condition occurs, that is when this lambda, that is the wavelength of the light, matches the circumference of the ring, resonant condition will occur, and when resonant condition occurs, light will travel through this resonator. Okay. So another way of saying this resonant condition is that the lambda, okay, the lambda will completely will uh, Let me clean it a little bit. It will completely fill your ring resonator. Okay, so this is, for example, lambda. So this is lambda, this is lambda, that is wavelength. This is another lambda wavelength. This is the wavelength lambda. This is also lambda. So it fits perfectly this wavelength. Wavelength is what? Distance, right? That is how many lambda? 1, 2, 3, 4, 5. This is 5 lambda. Okay, so 5 lambda fits in this. The real equation is like this, not lambda. It will be m lambda is equals to twice pi r eta. So that means the lambda, that is the wavelength, perfectly fits the circumference of the ring, and that way there will be resonant condition, and what will happen is that light will couple and starts to flow through the ring resonator. So is this clear? Do you have any question on this resonant condition, that why light will get coupled to the ring resonator? Instead of flowing directly through the waveguide, some of the lights at certain conditions, at certain wavelengths, they will get coupled to the ring. Did you guys understand this one up to this? Do you have question up to this? So if you have question, you can raise your hand. Otherwise, I'll move on. Uh, okay, I'm assuming there is no question. Okay, so assuming that you guys understood what happens at certain lambda, say lambda 1, your there will be coupling action will happen here, and light will starts to flow through the ring resonator. So if some light flows through the ring resonator, what will happen at the waveguide? What will happen at the waveguide? See, we are giving light as an input through this waveguide. Light is traveling through this part, and here some lights are getting coupled here. Okay, they are traveling through this path. Clear? So at this end, at the output, the intensity of the light will get reduced, right? Because most of the light, some lights are getting coupled through this ring resonator, and they starts to flow along this path, right? So lights are getting coupled here. So instead of flowing directly through this waveguide, lights are getting coupled here. So what will happen to the intensity at the output? The intensity will starts to reduce, right? At the output, at resonant condition, that means at the particular lambda, say I am sending a lambda 1. So at the output, the intensity will get reduced because not all the lights are getting passed now. Some of the lights are getting coupled to this ring resonator. Clear? Now see. For example, now I am sending a range of wavelength. Okay, a light having a range of wavelength. For example, lambda equals to 800 nanometer to lambda equals to, let's say, 1000 nanometer. Let's say 800, 1600. Let's say 800, 1600, 32, 32, 40, 48. Let's say up to 5000 nanometer. Okay, so this is the range of light that I am transmitting through this waveguide. So at resonant condition, which will be the resonant condition? Let's say 800 nanometer. So instead of 800, let's say 600. From 600 to 5000 at the output, at the transmission curve, this is your lambda, this is your transmittance. Okay, so let's say this is 800, this is 1600. Okay, this is 3200. This is 4000. This is 4800. Okay. So I've said that what resonant condition occurs at m lambda equals to twice pi r into eta. Okay. Let's say the resonant wavelengths are 800, 1600, 3200, and 4000 and 4800. So what does this mean? That means at these wavelengths, the light of these wavelengths will get coupled and starts to circulate through this ring. Is this clear? If you
Yes,
have
sir.
any question, you can ask. Okay. Uh, so that means what? At this wavelengths, your light will get coupled to the ring and starts to flow. So at these wavelengths, at the output, we'll get a dip in the uh, intensity, right? The intensity of the light will get reduced at this wavelength because at these wavelengths, lights are getting coupled to this ring resonator, right? And for the other wavelengths, and light for the other wavelengths, for example, wavelength, say in between this, say at 1,000 wavelength, at 1,000 lambda, this is equals to at 1,000 lambda, there will be no coupling, right? Because that is not resonant condition. At 1,000 lambda, what will happen, guys? What will happen at 1,000 lambda?
That the intensity of light will not change.
Yeah, because all the lights will travel through the waveguide. And so, for example, at 6,000 lambda, sorry, 600 lambda, again, there will be no coupling. All the lights will pass through this waveguide. Clear?
So is this because this is a non-resonant condition?
Yeah, because these are not non-resonant condition. Because I've said what? Say, twice pi r, let's say, into eta. It has to be equal to this value. Okay, m lambda should be equals to this value. So, but if this value is, for example, I've said that this value is 800. So if it's not equals to 800, then this will not be a resonant condition and all the light will pass through the waveguide. There will be no coupling action occurring here. Clear? Okay.
Yes, sir.
Yes.
No, I said yes, sir. I
Oh,
understood.
okay. So that means at the transmitted curve, what will happen? This is 800. So at the transmission curve, what will happen? Light will remain, for example, this is 600. At this point, the intensity of the light will be high. Okay, that means the transmittance value. That means all the lights are getting transmitted through this waveguide. So the transmittance will be, the value of transmittance will be high. But at 800 nanometer, there will be coupling occurring through this ring resonator and the intensity will get reduced. That means P naught value will get reduced. So P naught by P1, that is T equals to P naught by P1 will also reduce. So that means at 800 nanometer, your transmittance will reduce. Okay. So that means the curve will look something like this at 800 nanometer. Okay. Then again at 600 nanometer, this will be resonant condition. So it will look like this. It will look like this at 3200. It will look like this at 4000. It will look like this at 48,000. Clear? Because these at these points resonance is occurring and there is dip in the transmittance. Did you guys understand this? So
Yes, sir.
Yes, sir.
this is the transmission curve that we will actually observe. Okay, so this is what we want to see. That okay, where we are getting the dips. Okay, that means when we get this dip, that means we can actually formulate a lot of things from this transmittance curve. For example, if I show you from this paper, you see, uh, this is a structure. So in our case, it was a ring, right? In our case, we had a ring here, but you can actually take any types of shape. Okay, resonance will still occur. Okay, this is, for example, at that place, there will be an effective, the effective index, refractive index of this structure. We took an ring, but here we are seeing a pie-shaped structure, pie-shaped resonator. Okay, so the transmittance curve of this one looked like this. See, at 800, they're getting a dip. That means at 800 nanometer, they are getting the resonant wavelength is actually 800 nanometer. Also, they get another resonance at 400 nanometer, 1400 nanometer. Clear? So they get something like this. So what is this? So this you see the red line, the black line, it is for d equals to 0 nanometer. Red line, it is for d equals to 2 nanometer. So what is this d? So this is one of the application of the resonator. You see, this is actually your D. So this was your, I'm just showing you an application of the plasmonic resonator. So what they are saying is that they've given a pressure at this point. So due to this pressure, there is a deformation occurring. Okay, a deformation happens to this resonator. So that deformation is quantified by D. Okay, then how much deformation occur, how much it has reduced. For example, it has deformed up to this, it is D1. If it has deformed more, it is D2, and so on. Okay, so based on this deformation, you see, I've said what? The resonant condition twice pi r eta, that is the length of the length, that is um, the light will travel. Okay, so due to this deformation, okay, this is deformation, the your eta changes, your refractive index will change, your effective length will also change. So that means your resonant condition will also change. Clear? That means without deformation, resonance was occurring at 800 nanometer, right? But due to deformation, now the resonant condition has changed, and let's say it is occurring at 1000 nanometer. Clear? So due to deformation, the resonant condition changes. Okay, so this they have shown this for deformation. That is, they are applying pressure, deformation is occurring, and the resonant condition also changes. So this can also be applied for temperature. For example, if you provide certain temperature, your for temperature T1, the your refractive index will be eta 1. For temperature T2, your refractive index will be eta 2. So this will change based on your temperature. So if your temperature changes, your refractive index changes, and if your refractive index changes, your resonant condition also what changes. Okay, so if your resonant condition changes, your lambda will shift, the resonant frequency or the resonant wavelength will shift. That is what they have actually shown here. See, for d equals to 0, that means for d equals to 0, they are getting resonant at this wavelength, that is almost at 1425. Okay, now for d equals to 2, the resonance has shifted. You see, for d equals to, the resonance shifted to this point. For d equals to 4, the resonant frequency have shifted. They are shifting. Okay, so there is some shift there. The deep is shifting to the right side. Okay, this is maybe called red shift. Okay, that means these are shifting now. So now what will they do? What they will do is that they will calculate this shift. You see, uh, you see here they will utilize this equation del f by df. Okay, that f is the resonant frequency of the cavity, and df is the change in the frequency. Okay, so this is actually called the Slater's law. So from this, they can actually, with the help of some other equations, for example, these two equations, they'll actually quantify that from the change, that is from the del f, they'll actually get information of P pressure. Clear? There are some equations, for example, this Slater's law. Then you have this Pascal's law. Sorry, yeah, Young's modulus of the silver. It depends on different materials. So using these equations, what they essentially does is that from this data, that is from this del F data, they are getting this del P data. Okay, so from this they are getting the pressure that is applied. So that's why this is actually a pressure sensor. Okay, so the same thing you can do for the microring modulator. So did you guys now understand that what can be a possible application of this microring modulator? Did you guys understand this pressure sensor application? Any question on this? So again, I'm just saying you the simple thing, that is, see, from the data of uh, deformation, that is del D. From deformation, they found the change in resonant frequency, that is del F. Okay, from this information, they got this information, and from del F, they found the change in pressure del P. Okay, so applying pressure, they found this is deformation, and from this deformation data, they found the resonant frequency change data, and from that they got the change in pressure data. From that they can actually measure your pressure. So this is one of the application of the ring of this resonator, plasmonic resonator structure. So from the plasmonic resonator structure, they have created a plasmonic pressure sensor. So did you guys understand this one? If you have any question, you can ask. Okay, so I'm assuming no question. So we'll simulate this one, and after simulation, we'll actually get an idea of what is actually happening. Okay, so we will see the electric field spectrum, and then we'll see the transmission spectrum T. Okay, so now I request everyone to open the COMSOL software. Okay, from this point, I will show step by step how to do the simulations. So these simulations are almost identical for all types of simulations. Okay, the steps, they are almost identical for all the simulations. So you there is no need for you to get intimidated by seeing all the steps that are involved in such simulation, because once you do this simulation, they can be applied to any other simulations. Okay, they are almost similar. So did everyone open COMSOL? Okay, raise hand those who have opened the software. Okay, so from this point, I'll proceed through some steps, and I'll ask you guys to raise your hands, those who have completed those steps. Okay, and if you face any problem, you can just ask me, and I'll try to solve those things. Okay. Okay, it seems like only 6 people are attentive to this class. Okay, anyway, almost 12 people. So, okay, first, can you guys see this screen, the COMSOL software? Can you guys see this?
Yes, sir.
Yes, sir.
Okay, so the first thing you should do is open this model wizard. Click on this model wizard. And after that, click on this 2D simulation. This 2D. We'll be doing 2D simulation, not 3D simulations, because 3D simulations are computationally heavy. And the advantage of doing 2D simulation is that it gives you almost similar accurate result as 3D simulations, but with almost negligible time completion. With almost negligible time compared to the 3D simulation. The 3D simulations takes a lot of time, but 2D it takes a whole lot less time than these 3D simulations, but provides you with a more close results. Okay, so click on this 2D simulation. So did you guys get this? So did you guys found this select physics?
Yes, sir.
Okay,
Yes,
Yes,
nice.
sir. Yes, sir.
Okay, so as I've told you that we'll be simulating this Microring modulator. Okay, so our main target is to find this transmittance curve. Okay, to observe the electric field. Okay, the but the electric field associated with this light, because light is what, an electromagnetic wave, right? So our focus will be on finding what the behavior of the light in this ring resonator, that is in this structure. So that's why we'll first go to optics, then wave optics, and click on electromagnetic wave frequency domain, this EWFD. So select this one and then click on add. Once you click on add, it will come to this drop box here, the added physics interface. And after that, click on study. So first go to optics, wave optics, EWFD, then click on add, and then click on study. After this done,
Yes, sir.
okay, nice. Then click on this boundary mode analysis. So after clicking on boundary mode analysis, press done. This boundary mode analysis. You should select this boundary mode analysis. And then after that, press done, and you'll have something like this. So did you get this interface?
Yes, sir.
Yes, sir.
Yes, sir.
Nice. Now, you see the UI, that is the user interface of your console, is very simple. Okay, it's very user friendly. You see all these things in the model builder. See, these are arranged sequentially. Okay, so uh, for example, first you have to create the geometry, then add the materials, then do some simulation settings again, some uh, some study about the results. These are done all sequentially. Okay, so that you don't miss some steps. Okay, so it is very easier to keep track of keep track of the steps. Okay, so you guys got this right? Okay. So one thing that you should do is that first to observe the structure clearly is that go to sketch, because by default it usually remains on. By default it stays like this, right? So go to sketch and deselect this one, this sketch. Deselect this sketch option. Go to sketch and deselect the sketch option. Did you guys do this?
So can you repeat the step?
Go to sketch. Here, go to sketch and deselect this one. Maybe for your case, by default, it looks like this. But you just first deselect this one. So that this is actually an optional step so that you can clearly see the uh, structure here. Okay. So deselect this one first. So if it's done, our first step is to add some parameters. So what is parameters? Parameters nothing but variables. Okay. So in MATLAB, you used to create some variables, right? Like x equals to 5, y equals to 10, these types of things, right? And then you utilize those variables in the next part of the course, right? So the similar thing you will do in COMSOL. That is, you first define some parameters. Okay. So first, we want to give the parameter that is the radius of the ring. That is what? R. Okay. We want to give this parameter. So do it with me. So R, then in expression, let's say it should be 200 nanometer. The value will be there automatically. And description, it is like the comment. Okay. So just write uh, radius of the ring. So did you guys get it? So this is like just a variable. This R is now a variable, a parameter. It is having the value 200 nanometer. After this done, did you guys do up to this?
Yes, sir.
Okay, if done, then fill up the rest of the data, the rest of the parameters. You can fill this up. Can you guys see this?
Yes, sir.
Okay, if you guys can see this, then fill this thing up. This is the for now you don't have to write this. I'm just writing this so that you can understand. You just first fill up this thing, these two rows. Okay, this R H1 A W lambda 1 lambda 2 lambda 0 F1 F2 F0 and N. Okay, so once you are done with this, raise your hand. Those who have done this, done up to this, raise your hand. So again, try to fill this one. And if you are done, raise your hand. Okay, so uh, I think almost those who are actually active, I think they have already done it. So okay, uh, up to this done, right? কোথায় গেল? Hmm, I see. Okay, so I'm moving forward. Now listen. So the parameters are defined now. Okay. So the next step is to draw the geometry. So first go to geometry. First go to geometry and see this length unit. Okay. So select it to nanometer so that even by mistake if you don't if you don't define the unit, there will be no problem. Okay. So in geometry, go to geometry and select the length unit as nanometer. Okay. After that, right click on geometry. Right click on this one and see there are some options, that is circle, ellipse, rectangle, square. Okay, so click on circle. Yeah, sir. First click on this rectangle. We want to create the substrate first, that is uh, this one. Okay, first we want to create this rectangle. All right, so what should be the width of the rectangle? In the parameters, see, I have defined width of the substrate is W, height of the substrate is H1. Okay, so I'm showing you again. Go right click on geometry and then click on rectangle. Okay, if I'm going too fast, you can just stop me and ask me that where you are stuck. So then go to rectangle. Width will be W, height will be H1, and this position. Okay, first do this one and then click on build selected. Did you guys find something like this? কেউ একজন মাইক অন করে
Yes, sir.
একটু রেসপন্ড করো
Yes, sir.
কন্টিনিউয়াসলি।
Yes, sir.
আচ্ছা, so then click on this one, zoom extents. So you'll find the whole uh, rectangle here, this substrate. Did you guys find this one? Okay. Now see
Yes, sir.
here the position, the base, it is corner, right? And the coordinate is 0, 0. That is x is 0, y is 0. You see this corner, you see what is the coordinate of this corner? It is at y-axis, it is 0, at x-axis, this is also 0, right? So that means the position of the corner is at or at the origin 0, 0. Okay. So it is better, it is easier, actually not better, it is easier to work with center. Okay, if you guys give now select the center now and keep the x and y 0, the center will now be shifted to 0, 0. So again, after after selecting the center here, click on build selected and then press this button, zoom extends, and you'll see now the center has moved to 0, 0. You see y-axis 0 is here and x-axis 0 is here. So up to this done.
Sir,
Yes, sir. Yes.
জানতে পারি
হ্যাঁ বলো, বুঝিনি,
rectangle-টা।
শুনতে পারিনি, ক্যান ইউ প্লিজ সে अगेन?
Sir, width আর height-টা সেট করার পর আমি rectangle-টা কিভাবে আনবো?
Did you click on this one, this zoom extends? Try to click on this one and see whether it appears or not.
No, it doesn't appear.
আসে না?
No.
You see in parameters check, W is 1000 nanometer, H1 is 800 nanometer. Okay, and in geometry, in rectangle, okay, width is W, height is H1, your base is center, these are zeros. And then click on build selected. After clicking on build selected, if you press this one, zoom extends, it is supposed to come.
Okay, হ্যাঁ এখন এসেছে।
Okay, nice. Now we want to, what is the next step? The next step is to form this ring, right? So there are two circles, right? This is one circle with radius r, and then this is one another circle. So what is the radius of this circle? You see here, see, thickness of the ring. This is a. Okay, that means this thickness is what? This is a, right? So what would be the radius of this circle?
R
168.
minus A.
R
R
minus a,
minus A.
right? So first go to geometry. Again, right click on this one and select circle. So once you have selected the circle, at the radius, give R, and base should be center. Okay. So after that, if you click on build selected, the circle will come here. And this sector angle, this is 360. This is 360 means and whole circle will be created. For example, if I give it at 180 degree and give build selected, see only a half circle is created. Okay. So keep this 360 and click on build selected. You'll find this circle here. Then again, right click on this one and create another circle. And now the radius of this circle would be r minus a. And if you give build selected, you'll form the ring here. So do up to this. And once you are done, raise your hand. Okay, very good. So now you have this this ring, this substrate. The next step is to form the what? The waveguide. Okay, so again, right click on this one, create a rectangle. Give the what should be the width? The width should be the same as the substrate, right? So the width I'll give as W, and height, let's say the thick same as the thickness of the ring, that is A. So build selected. So see it, and this one should be center. The position should be center. So now give build selected. So this is now here. So what I want you guys to do is that bring it from here to here. So how can you do this one? Any idea?
Change the y-axis.
By changing the y-axis value
Exactly.
maybe to 300.
Yeah, exactly. So don't use values, hard coding. Use variables. You have set some parameters here, right? So 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 now your uh, waveguide is here. So you need to bring it here. So if you bring it by minus r, that is by this radius of the circle, so it will come to this position, right? Because the center will move, right? The center will be at this position, the radius of the ring. So if you move a little bit more, let's say the thickness of the radius, it will come back to this position. So here in the y, if I give minus r, if I give minus r, been selected, see, the center is at the radius. That means in this position, the center. Okay. See, the center is here now at this position. That's why the your waveguide is in this position. So if I move it a little bit lower by a, see, it will come back to this position. So give the y-axis value as minus r minus a. You can also do one more thing, that is to control this gap size. Okay, so what you can do is in the parameter section, select G. Let's say we're defining another parameter that is G, and let's say uh, what should be the width? You see in this rectangle, if I give a by 2, okay, This is now exactly touching the ring. This is a simple geometry. R will bring it here. If I move by thickness, if we move the center by a by 2, it will directly touch the ring. Now we want to create a gap between this ring and this uh, uh, waveguide. So we'll create a new parameter that is, let's say G. Uh, let's say we'll move it by 10 nanometer. Okay, this is gap. So now going back to rectangle, if we lower it by G, you see build selected, you see it has lowered by uh, 10 nanometer. Now what I can do is that for example, if I want to uh, increase the gap, so just by simply changing the parameter, and now if you just select build all, you see this one will get lower a little bit more, right? So parameterization is a very important thing. So it actually makes your work easier. So write like this: minus R minus a by 2 minus G. So G is the gap between this ring representative and the waveguide. So up to this done. Anyone struggling or left behind? Done. Someone please respond.
Yes, sir.
Yes, sir.
Yes.
Okay, nice. So now we have this structure. Our structure is done. Okay, we got this. We got this structure, right? It is done now. So what is the next part? You see, in COMSOL, it's already there. That is, the next part is the material. Okay, so we need to add material. So what are the two materials that I've said already? There is silver and air, right? So right click on material and click on add materials from library. Right click on materials, then click add materials from library. So you at the right hand side will find this add material library here. Okay. So and under the section built in, under this section built in, you'll find air. So select this one. Okay. Then under the section optical inorganic materials, you'll find silver. Select this model, Lawrence root model. Rackage Lawrence root model. Select this one. Mm. So what is this Lawrence root model? Why are we selecting this silver? There are other models. For example, this Johnson and Christie model. Then there is uh, this is the most common one. This Johnson and Christie model. This Rackage Lawrence model. So Rackage is actually he's some guy Rackage. He actually modeled this silver. He actually formulated this silver using this Lawrence root model. So the Lawrence root model is actually a mathematical description of how a metal's electron will respond to electromagnetic fields, right? So we are actually by when we are saying that I'm passing some light, what we are actually doing, we are actually uh, we are actually providing some electromagnetic fields, right? So this Lorentz root model is actually defined how a metal's electron, that is how a metal, or for example this silver, how this silver will respond to the electromagnetic field. This concept is actually defined by this Lorentz root model. Okay. So Rackage he utilized this Lorentz root model to formulate this silver. For example, Johnson and Christie, they didn't use any model. Okay, Lorentz root, for example, he utilized Rackage he utilized a theoretical model. That is this Lorentz root model. But okay, but but Johnson and Christie they utilized that from the experimental data. They did some hands-on experiment, and from that they have found the uh, characteristics of the silver. Okay. Just 1 minute, I actually got a call. Okay, so did you guys do up to this? Now double click on this silver, that is the wreckage. So this one will come here. So did you guys do up to this?
Yes, sir.
Okay, so now you have this. So now close this one. So you have this air, this silver, right? In the material, under this material section, you have this air and this silver. So now you see this air. So it is already applied to all the domains here. All right. As you can see, all the domains are highlighted by blue. And if you go to silver, this is not highlighted. That means silver is not applied here. See, in the domain, there is no number of the domain names are not present here. But see here, if you select on air, all the domains are present here. So we need air only in these portions, right? Only this resonator and the waveguide. We need air only in this portion. The other, this one will be silver. This one will be silver. This one will be silver, right? So what you should do is that if you just click on this one again, the air will get removed. See, if I'm clicking, just simply clicking again, you see in the domain only domain 2 and 4 is selected. For air, only domain 2 and 4 is there. And if you just click on again, the air from the other domains will get removed. So could you guys do up to this? Could you guys do this?
Yes, sir.
Acha. Then click on silver. And now if you click on this portion, you see in this domain, the domain 3 is selected. That means now silver is applied to this domain. See, it is highlighted by blue. Again, if you click on this one, it is highlighted by blue. That means silver is now placed on this portion. Again, if you select on this one, you see now this one, and this one is filled with is made of silver. That is, you have assigned materials to these structures here. You see. So when you select silver, you see these portions are highlighted by blue. That means silver is there. That means 1, 3, and 5. And if you select on air, you see only these two are highlighted by blue. That means air is on these two structures. So could you guys do this? This is air. This is silver. Air and silver. Sorry. So up to this done.
Yes, sir.
Or did you guys face
Yes,
any
sir.
problem? So be careful. This one is actually important. If you mess this up, there will be errors in your simulation. Your structure will look like this. When you click on air, these two portions are highlighted and the other portions are not highlighted. That means air is on this one. That means 2 and 4. Again, if you select on silver, these portions are highlighted. 1, 3, and 5. Domain 1, 3, and 5 are now silver. And domain 2 and 4 is now domain 2 and 4 are air. Okay, make sure your structure look like this. Okay, now moving to the next step, that is this electromagnetic waves frequency domain. Okay, now here we need to assign some boundary conditions. So what are boundary conditions? So you see these structures that we are now simulating, this is a two-dimensional structures, right? And COMSOL will only simulate this portion. But in real life, what happens outside this portion? In real life, outside this portion, there are some environmental conditions, right? There are some effects of the environment. We actually need to consider those things. But if you just simulate now like this, COMSOL will not consider those environmental conditions. So you actually need to define some bound. Those environmental conditions are usually replicated by this. You are usually assumed by this boundary conditions. So one of the boundary condition is this scattering boundary conditions. So in real life, what happens when you pass light through this waveguide? Some light will get scattered. Yes, light will confine here, couple here, and from here some light will get scattered out of this structure. So that's why you have to first right click on this electromagnetic waves, select the scattering boundary condition. Okay, select this scattering boundary condition. So you'll get this one here. After that, select. So we'll pass what was our objective? We pass light through this port and get output from this port, right? So apart from these two ports, that is, this is port 1 and this is port 2. Apart from these two ports, the other ones should be scattering boundary conditions. You should apply the scattering boundary conditions to the other surfaces. So select these ones here. Select this one's blue. This one should be also scattering boundary condition. This one scattering boundary conditions. And here we should also apply scattering boundary conditions. So apply the scattering boundary conditions to these surfaces except for these two. This one and this one, except for these two, apply the scattering boundary conditions for the other surfaces. Here, as you can see here in this box, you can see 1, 2, 5, 7, 8, and 10. Okay, so do up to this. Once you are done, raise your hand. If your structure look like this, you see, these are highlighted by blue. That means your scattering boundary conditions are applied here.
Sir, can you repeat?
Okay, see, I'm deleting this again, just to show you again. Right click on this electromagnetic wave frequency domain. Click on this scattering boundary condition. Okay, once you have created it, click on this one and just select the surfaces apart from these two surfaces, not this one. Do not select this, don't select this one. Also don't select this one. Just the other surfaces. For example, this surface, this surface, this surface, this surface, this surface, and this surface. So did you get it now? You see, here the boxes 1, 2, 5, 7, 8, and 10.
Yes, sir. Thank you.
Okay. Now we want to provide this light, right? We want to provide light from this port to this port. So we need to define these two ports. So the next step is to again right click on these electromagnetic waves, click on port. You see port here. Click on port. So once you have clicked on port, select this port because this is the input port. So first select this one. You see an arrow will be shown here. Okay. So once you have done this, again go to electromagnetic wave frequency domain, right click and again select another port. Okay, you see port 2 has come here now. So this is port 2. So after finding port 2, just select this port, that is this surface. Okay, so this, you see the arrow should be now pointing outwards. So when you click on port 1, the arrow is pointing inwards, and when you click on port 2, the arrow should be pointing upwards. So do up to this. If you face any problem, just ask me. So some of you might face problem selecting this one. So what you can just do is just zoom in, select this one, zoom in here, and select this port. Okay. So up to this done. Or anyone facing any problem?
Sir, can you repeat the port part?
Okay. First, I'm deleting the ports again. You see, delete. EWFD, right click on this one, select the port. Okay. So now this port 1, the port 1 has appeared here. So select this port 1 and click on this portion because light will give the input light through this port. So select this one. You see an arrow has come and it is pointing inwards. Okay, Then again go to EWFD, this one, and right click and select port. Okay, then now port 2 has appeared. So after clicking on selecting port 2, just select this boundary, this surface. And if you are failing to find this one, just zoom in. Okay, just click the zoom button here, zoom box, and just click on this one. You see now the arrow is pointing outwards. That means this is the output port. Could you do it now?
Yes, sir. Thank you.
Okay, very good. So now your ports and scattering boundary conditions are defined. Okay, so after this, done. Now the next thing is this mesh. Okay, so one thing actually I failed to mention is that what is this mesh? Uh, in, uh, you see, COMSOL actually utilizes, as I've told you in the earlier, in the very beginning of this lab, is that what COMSOL actually does is that it actually solves various numerical equations, right? It solves various wave equations, the wave equations associated with this structure. Okay, it solves the wave equations associated with this structure. So how does it do? It actually applies a uh, method that is called FEM, or finite element method. Okay, this FEM method. So what happens in that FEM method is that it actually divides your whole structure into this numerous triangular structure, triangular small structures. These are some subdomains. Okay, this whole structure, it is divided into these smaller triangular subdomains. You see, these portions are very small triangular regions. These are large triangular regions. That means the results from these regions will be more accurate because these are more finer triangles. So then he'll solve, their COMSOL will solve equations, more equations in these regions. Okay, you see. Uh, So what it does is that it divides the domain of the problem into collection of subdomains. Okay, these are the subdomains, these small triangular regions, these are subdomains. And each subdomain is represented by a set of element equations. Okay, these subdomains will be represented by, for our case, it will be represented by several wave equations, numerous uh, differential equations. Okay, and then he'll solve for those equations. He'll solve those equations for these smaller subdomains. Okay, then at the end it will systematically recombine all sets of element equations into global system. That means for each subdomain it will first solve the equations, and then it will recombine all the results of these subdomains and give you a final calculation. Okay, so this is actually your finite element method. You see, FEM mesh. So this is called actually meshing these triangular regions. Forming these triangular regions, these are called meshing. So our next step should be to create this mesh. Okay, so first click on this mesh and then right click and select free triangular. Okay, click on free triangular. So did you guys done? Are you guys done up to this? So once you have clicked on free triangular, click this one. Select domain. From here, select domain. Geometric entry level. Select domain here. So once you have selected the domain, then select all the domains here. Select all the domains, 1, 2, 3, 4, 5. All these domains, select this one. So again, click on mesh. That